Hopefully by now you have finished your areas from 0 to 0, 0 to 1, 0 to 2, 0 to 3, 0 to 4, and 0 to 5, and gotten the following area values. Now, observationally, the answers to letters C and D were hopefully relatively obvious, but maybe hard to put in words. So let's just make sure that we articulate them in a way that can help you solidify those thoughts. As x gets larger, the value of the integral, in other words, the value of the area, gets bigger as well. So the value of the integral gets larger as we extend the x coordinates, as we accumulate more space under the curve. So in question letter D, where it says what's accumulating here, we are accumulating area under the curve. If you only allow us to go from 0 to 1, you're only allowing us a very small space. But if you allow us to keep gathering more area from 0 to 2, we can work with more space. From 0 to 3, even more space. 0 to 4, 0 to 5. What if we go beyond? If you allow us to accumulate more area past 5, maybe it's 6 or it's 7 or at 8, I can get more and more area under the curve. So accumulating is really just trying to gain as much as you can. And the longer we can stretch our x coordinates, the more area we can accumulate. If that sounds really obvious to you, that's good, because the concept of accumulation is very basic. Essentially, the bigger a space you allow yourself to calculate, the more area you're going to find there. It's not exactly a super complicated concept. Now, importantly, the idea that we've done this as an area problem should also link us back to the idea that this is, after all, a calculus problem, and that we could have done any of these problems with calculus. In fact, it might have been kind of obvious to you that the answers in the table were 0, 2, 4, 6, 8, 10, because the calculus here kind of links itself. And I'll do one of these examples. I'll just pick a random one with calculus so that we can see why that would work. I just happened to pick the integral from 0 to 2. Could have done any of them. But if I had wanted to do the integral from 0 to 2 with a calculus approach instead of an area approach, I could have, because they gave me that the f of t function is 2, and I could have plugged that in for f of t, so a direct replacement, if you will. I replaced the function f of t with the number 2, since they told me in the original question that that was equivalent. If I do this actual antiderivative, this would be the antiderivative of 2 dt, which is 2t. Implicit tips me off that the variable is t, evaluated at 2 and at 0, which we can definitely do. 2 times 2 plugged in would be 4, minus 2 times 0 plugged in would be 0, 4 minus 0 is 4, and sure enough, in the table, that is what I got when I did an area as well. We're not surprised to see that. But did you notice how the antiderivative was 2t? And did you notice that if I do an antiderivative for every other problem, it would always be the same? I mean, if I did from 0 to 1, it would be the same integral, the integral from 0 to 1 of 2 dt, which is still 2t, just evaluated at different limits. And no matter which one I pick, even if I picked one down at the end, the integral is still going to be the exact same integral. It's the exact same function. It's still 2t, and the only difference is that we're evaluating at different limits. So the fact that the function is always 2t is kind of useful, because notice, 2t is just double of t. That's what's been going on in this table the whole time. If t is 1, double it. T is 2, double it. T is 3, double it. T is 4, double it. T is 5, double it. I didn't have to do this as an area problem. Could have noticed that pattern. But it does reiterate the connection between doing integrals and doing area problems. You're getting the same pattern because you're actually just working with the exact same mathematical idea. It looks different when you take an antiderivative, but at its core, the antiderivative is really giving you the same answer as an area problem would. So it's nice to know that that idea is still kind of circling back around. Now, question number 2 is very similar. In fact, so similar that I'm going to ask you to try it as an exercise on your own. question number 2 is giving you another function and asking you to determine the values of the integral from 0 to 0, 0 to 1, 0 to 2, 0 to 3, 0 to 4. Now, just so you're not completely on your own, I'll at least help you set up the picture, and I'll encourage you to think about which way, given the picture, you'd prefer to do this problem. The function in this one is 2t, which would be a diagonal line with a y-intercept of 0 and a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. If I graph it, it looks like I get a relatively nice looking geometric shape. We'll end up with triangles if we break it down from 0 to 1, 0 to 2, 0 to 3, 0 to 4. So if you feel comfortable finding the areas of these shapes as triangles, great. If you feel more comfortable finding these as actual antiderivatives, the antiderivative of 2t evaluated at 0 and 0, the antiderivative of 2t evaluated at 1 and 0, integral of 2t evaluated at 2 and 0. If you feel comfortable doing that repeatedly, you can do that too. That'll be your choice. But hopefully you'll get these values. You'll be able to think about these values, and you'll again be able to ask yourself, why do those values make sense? So between now and the time you start the next video, fill in that table of values, either finding areas or finding antiderivatives, and see if the answers that you get make sense in the bigger context of this connection.